Hello, this is video number 30 on my multivariable calculus course. In this video, we're going to talk about surface integrals of vector fields. So just remember that when we talked about line integrals, we had two different kinds of line integrals. We had line integrals of scalar functions, and we had line integrals of vector fields. So we have these two types of line integrals. The first one evaluated the total mass of a curve when the density was the integrand. The second one evaluated the work. And the second line integral depended on the orientation of the curve. Now, if you were trying to evaluate surface integral of a vector field, we need to have an orientation for our surface. So we talked about surface integrals of scalar functions with respect to area. Now we want to talk about surface integrals of vector fields. So this is what we're going to talk about. Now first, what does it mean to have the surface area of a vector field? So what we're trying to do is we are trying to figure out how much of the vector field is going through this surface per unit time. So what does that mean? It means we need to have two sides of this surface, side number one and side number two. So we have two sides to this surface. But what does it mean? How do we mathematically define two sides of a surface? Well, in order to define two sides of a surface, we need to define some sort of a direction. So what does that mean? We need to define and we need to find a way that we can say the right side, left side, or side on top or side at the bottom, side one, side two. So how do we say that? Well, we can say that we can denote an orientation of a surface by a bunch of normal vectors to that surface. So unit normal vectors that they change continuously as we move along the surface. But isn't that true for every surface? Well, not quite. If you look at a piece of paper, a piece of rectangular piece of paper, and then take two sides of this and glue them in the opposite direction. So glue this one, this vertex to this vertex, and glue this vertex to this vertex, and glue this edge to this edge. You get what we call a Mobius strip. This Mobius strip only has one side as illustrated in this diagram. So if you start from this point and go along this surface, then you're going to come back. This is a normal vector in the first one. Then you're going to come back as a normal vector in the opposite direction. So there is no way um, to define a bunch of normal vectors that vary continuously as you move along the surface. So this surface, the Mobius strip has just one side. Okay, so now we're going to talk about how to take the surface integral. So an orientation of a surface sigma is a selection of unit normal vectors n for each point on the surface in which n varies continuously. Okay, let's talk about surface integrals of vector fields. So what are we trying to do? Given a surface, we are trying to figure out how much of the vector field is going through that surface. How do we do that? Well, the vector field is going to change at every point. Let's say your vector field is given by a velocity. So what are we trying to do? We are trying to find out how much of this is going through this surface. In order to figure out how much of this is going through this surface, we'll have to figure out the volume of the fluid flow that is going through this surface. So because I'm trying to find the volume, I'll have to find the area of the base and multiply by the height. So the height would be evaluated by this quantity. This would be the height. So let's say the unit normal vector is n. The height would be, so after 1 second, and this v is the velocity. After 1 second, the height is going to be magnitude of v times cosine of theta. which can be evaluated by dot product. So dot product of v and n divided by magnitude of n. So now if n is a unit normal vector, this would be v dot n. So this gives us the height of the liquid that is going through this surface. And I'm assuming that I'm looking at a fluid going through a surface. Now, because the height is that amount, we can find the volume that is going through this surface by multiplying area. So delta S, let's say the area is delta S. We can multiply the height, which is v dot n. This is the height, by the area, by delta S. So this is the volume that is going through this surface. Now let's say delta of xyz is the density function. At every point, this liquid has some density, which may or may not be a constant number. So if you take the density and multiply by the volume, then we get the mass. So we get the mass going through the surface per unit time would be density times volume. So this is volume and this is density. So mass would be this, and we have to take the total. So we get this formula. So the surface integral of delta, which is density, times times this one, which is area, which is volume. So area is just ds, and then we take the total. So this is the total mass that goes through the surface per unit time. How do we evaluate this line integral? So this was just one example, surface integral, and this was just one example of a surface integral. In general, we think about this density times velocity as our vector field. So in general, we can evaluate the surface integral of f dot n ds by replacing the formulas. So what we know is that ds is magnitude of RU cross RV dA. This is something we have talked about before. And we also know that the normal vector, the unit normal vector, is RU cross RV divided by its magnitude. So when we multiply these two, we get NDS is equal to RU cross RV dA. And this can be used in evaluation of f dot n ds. Another way of denoting this would be, instead of writing down nds, we can also write down ds, where s is in bold, or sometimes I put arrows on top. So n dot ds, or nds, is sometimes denoted by d with an s on top. Okay, so now we're going to do a few examples. So the first example is this. Let a sigma be the sphere that's oriented inward. Evaluate this surface integral. Okay, so I'm going to go ahead and parameterize the surface. That's the first thing we need to do. And the radius is 3. So what is the parameterization? We have to use phi and theta. The x component is 3 sine phi cosine of theta. Y component is 3 sine phi sine of theta. And the z component is 3 cosine of phi. So these are, this is the parameterization. Phi goes from 0 to pi, and theta goes from 0 to 2 pi. Next, we're going to have to find the parameters, the cross product of r phi cross r theta. And this is something we have done before. So if you recall, this was rho sine phi, so 3 sine phi. We did it in an earlier example. So it's rho sine phi times xyz times 3 sine phi cosine of theta, 3 sine phi sine of theta, 3 cosine of phi. Okay, so we have to evaluate this one, which we have done this before. Now we'll have to find the orientation. They told us that the orientation must be inward. So we'll evaluate the orientation. We'll take a sample point and we'll evaluate the orientation at that point. So at that point, at point 0, 3, 0, any point would work as long as this normal vector is not 0. So at this point, phi is going to be pi over 2 and theta is also pi over 2. So what do we get? R phi cross R theta is going to be, well, 3 sine of phi, so that's just 3, because phi is pi over 2. 3 sine of phi cosine of theta, that's 0. 3 sine of phi sine theta, that's also 3. And 3 cosine of phi, that is 0. So when you look at this vector, this is 0, 9, 0. So this vector is going in the positive direction of the y-axis. So this is outward. So this is outward. And recall that we draw normal vectors from the points on the surface. So since this is not matching the orientation, so we need to use the negative of that, to use r theta cross r phi. So not r phi cross r theta. So we'll have to evaluate the surface integral that they gave us, which was z squared k dot ds, or sometimes written as dot n ds. So this would be surface integral. Well, we'll have to evaluate z squared k. Well, z is right here. So this is z. 9 sine phi cosine phi. So that is z. And then we'll have to square that. And then k dotted with, well, what is normal vector? Normal vector is what we found here. It is this one, but we'll have to negate that. So it is negative 3 sine phi, and then multiplied by 3 sine phi cosine theta. So I'm going to move this down, continue here. 3 sine phi sine theta and 3 cosine phi, all of that d phi d theta. And the limits are from 0 to pi and 0 to 2 pi because it's a full sphere centered at the origin. Okay, so the rest is computation of the integral. So 0 to 2 pi, 0 to pi, this would be 81 sine squared phi cosine squared phi. So because this is an inner product, I'll have to multiply only by the third component. The other two are going to become 0. So multiplied by this one, so that would be 3 cosine of phi, d phi d theta. So this gives us the integral from 0 to 2 pi, integral from 0 to pi. When you multiply by 9, you would get 9 and 72. It's also a negative sign. We get sine cubed phi cosine cubed phi, and then d phi d theta. Okay, so how do we evaluate this integral? Well, the integral, because the exponent of sine and cosine are both odd, we could use u equals sine or u equals cosine. Both of those two are going to work. So we'll get it started and I will let you finish up the solution. So we write it down as sine of phi times sine squared, which is 1 minus cosine squared phi, times cosine cubed phi d phi d theta. Now we are going to use u substitution. So u equals cosine of phi, du equals minus sine phi d phi. So this would be integral from 0 to 2 pi. So when you plug in phi equals 0, we get u equals 1. When we plug in phi equals pi, we get u equals negative 1. Minus 729. Okay, so sine of phi times d phi is going to be minus du. So I can drop the negative sign and replace these three things minus sine phi and d phi by du. So we'll do du right here. And the rest would be 1 minus u squared times u cubed and then d theta. And this is a very easy integral to evaluate. 0 to 2 pi. Once you multiply, it is going to be just a polynomial. And we can put the 729 outside of the integral. So u cubed minus u to the fifth du d theta. And I will let you compute this. Okay, so the next question. Let sigma be part of the paraboloid that lies below the xy plane, oriented upward. So we have a paraboloid. The vertex of this paraboloid is at -4. So portion of this is below the xy plane. And this is the portion that they are looking at. They are looking at only this portion of the paraboloid. So this is the portion they're looking at. And the orientation is upward. So the orientation is upward here, here, and here. So we are trying to find a surface integral. So the first thing we need to do is to come up with a parameterization for this surface. So what is a parameterization for the surface? We could parameterize it because this is z equals x squared plus y squared. We could say it is parameterized by r of xy equals x, y, x squared plus y squared minus 4. Now, where do x and y come from? X and y are inside the disk x squared plus y squared less than or equal to 4. And let's call this disk R. So I'm going to draw that here. This is R. It's of radius 2 centered at the origin. So x and y come from here. Okay, so we can go ahead and evaluate Rx. Rx is going to be 1, 0, 2x. Ry is going to be 0, 1, 2y. And then the cross product Rx cross Ry is going to be, if you eliminate the first column, we get 2x minus 2x. Eliminate the second column, we get minus 2y. Eliminate the last column, we get 1. Now, looking back at the orientation that they gave us, they told us it's oriented upward. So upward means k must be positive. Positive. So which is upward. So what does it mean? It means we don't have to negate it. We could just use that one. So the surface integral of x squared I plus y k dot ds is going to be double integral over the region that they gave us, x squared I plus yk. Now the orientation was in terms of x and y. Sorry, the parameterization was in terms of x and y. So we don't need to substitute z. There is no z in here. Dotted with normal vector is -2x, -2y, and 1. And then we'll have to integrate over this region. Now this region is a polar region, so it's better not to switch to Cartesian. So we're going to find the dot product. We get -2x cubed. That's the first component. The second component of the first one is just 0, so like it would just give us 0, so plus 0. The third component would be plus y, and this dA. Now this is a polar region. It is, we can evaluate that by switching to polar. The radius of this circle is 2, so we can do -2 r cubed cosine cubed theta plus r sine theta. The radius is 2 and it's a full circle, so r dr d theta. So it's from 0 to 2 pi and 0 to 2. And this is a relatively easy integral to evaluate. So this would be from 0 to 2 pi, from 0 to 2. Multiplying by r, we get -2r to the fourth cosine cube theta plus r squared sine theta dr d theta. Integral with respect to r is pretty straightforward. Integral with respect to theta, so I will let you evaluate this one, but integral with respect to theta, this one is easy to evaluate. This one, you'll have to do a u substitution. So for cosine cubed theta d theta, what you do is you write it down as sine theta times cosine squared, and we can write down, cosine theta times 1 minus sine squared theta d theta, and you do a u sub for sine of theta. And once you do this u sub for sine of theta, both limits of integration become 0. So in fact, this final answer would become 0. One of the things that we saw here is if you look at a function that is of the form z equals f of xy, a simple parameterization is often r of xy equals xy f of xy. And we can use that to find the normal vector. If you find r sub x, that becomes 1, 0, f sub x. R sub y becomes 0, 1, f sub y. And once you find the cross product, you get minus fx, minus fy, and 1. This is a formula worth remembering. Okay, one last example on this one. Evaluate the surface integral of zk ds where sigma is part of this cylinder between z equals 0 and z equals 1. Okay, so we're going to graph the surface, and they also told us that the orientation is outward. So this is the orientation for the surface. So here it would be like to the out of the board, out of the screen. Okay, so the first thing we want to do is to parameterize this surface. So what is the parameterization? Well, one of the parameters would be theta and one of them would be z. And radius is 1. So it would be cosine theta, sine theta, and z. Theta would range from 0 to 2 pi, and z would range from 0 to 1. So the top is 1 and the bottom is 0. Next, we're going to have to find r theta. That would be minus sine theta cosine theta 0. Rz, that would be 0, 0, 1. Then we find the cross product of these two, r theta cross rz. Eliminating the first column gives us cosine of theta. Eliminating the second column gives us sine of theta. And then eliminating the last column gives us 0. Then we'll have to check the orientation. So if we check the orientation, let's say it doesn't really matter what point you take, but I'm going to take maybe this point right here. So let's take the point. This point is 0, 1, 0. So what is theta? Theta is pi over 2 because it's on the y-axis. Y-axis theta would be pi over 2. And z is of course 0 because it's on the xy plane. But there is no z in there anyway. So r theta cross rz is going to be 0, 1, 0. So 0, 1, 0 is going to the right, which means this is outward. So it doesn't need to be negated. So which is outward. So we don't need to negate. Next, we're going to have to plug it into the formula and evaluate. So the surface integral of zk dotted with ds is going to be, so limits of integration for z is going to be 0 to 1, and for theta is going to be 0 to 2 pi. Zk dotted with the normal vector. The normal vector is cosine theta, sine theta, 0, and then dz d theta. Now, fortunately, the integrand is just 0. When you find the dot product, you'll have to multiply the third component with the third component. So this is just 0. To summarize, what we did was we talked about surface integrals of vector fields. In order to evaluate surface integral of a vector field, we need to find a parameterization for the surface sigma. Then we need to evaluate RU cross RV and make sure that the orientation matches the one given in the problem. If it does not, then we'll have to find the cross product of RU and RV. And then sometimes this NDS is written as DS with bold letter S, and that's evaluated by RU cross RV dA. And then we change du dA to du dV, dV du, or R dr d theta. Using the parameter region in the UV plane, we can evaluate that double integral. When the surface is given as z equals f of xy, a possible parameterization is r of xy equals xy f of xy, and in which case we can use the normal vector negative fx, negative fy, 1. But we have to always check the orientation at the end. One other thing before I end the video is that this surface integral is often called Flux integral. Flux integral, or flux of f through sigma. I will see you in the next video.